Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the third lecture on the marine renewable energy systems. In this course, we are going to discuss about analysis, design and development. The course being offered under SwayamPrabha portal by Department of Maritime Engineering at IIT Gandhinagar. Myself and Dr. Patil are together doing this course. In the last lecture, we discussed about the importance and the factors which affect the fundamental primitive design of wave energy converters. Let us start from that point. So, we will say lecture number 3. Here in this lecture, we will talk about details on power take-off mechanisms. So, we will discuss only the primitive concepts of PTO. Then later, as we proceed with the design of energy converters, appropriate PTOs will be discussed and design concepts will be explained then and there in those specific lectures. So friends, there are some myths which people have in mind about wave energy converter. Before that, we look at what we learned so far we learned that wave energy converters or energy conversion or renewable energy can come essentially from three sources: waves, wind, and let us say solar, the premium sources, out of which wind and solar are most promising and more popular in different parts of the world, even in India on the coastal sites, especially in Gujarat and Tamil Nadu. However, when you talk about wave energy converters, there are restrictions, because the fundamental myth in this design is wave energy converter success depends on the design. It is design dependent, it is site dependent, and therefore there cannot be a uniform global design of wave energy converter. However, there can be some fundamental designs available for wind and solar powers. It is because of this exclusivity in wave energy harvesting, we are facing difficulties in designing a global design for wave energy converters. The second issue what we discussed was, generally people think if you want to harness wave energy, I should have a system which is very stable, very stiff, and therefore it should be able to or capable of harvesting energy. You know, energy harvest from waves can happen in different degrees of freedom. It can happen in translational degrees, it can also happen in rotational degree harvest. So, yesterday we discussed about different translational degrees as surge, which is displacement along x axis, sway, displacement along y axis, and heave, displacement along z axis. Rotational as well, about x axis, which we call as roll, about y axis, which we call as pitch, and about z axis, which we call as yaw. Interestingly friends, when a body is freely floating in space, at least 2 degrees will be coupled. At least 2 degrees will be coupled. It means you cannot have an independent motion amongst all these 6 degrees. See, this coupling effect is the one which can compromise on the energy efficiency of harvesting wave energy devices. So, therefore, one has got to think about the design appropriateness when we choose a geometric form. Therefore, friends, we understood that the design of wave energy converter is geometric dependent, what we call form dominance. So, the design is form dominant, and further wave energy converters need not be fixed type. Fixed type converters are suitable only for shallow waters, and that too the design is more complex because instead of harvesting wave energy, the system has to sustain the lateral loads coming from winds and waves. So, it becomes a system design or structural design for waves, but not for harvesting. Why I am saying this? Please recollect the statement what we made in the last lecture. When I want to have the maximum efficiency of a WEC, it is very interesting to note that WECs are designed to resonate with the input frequency. That is a very interesting problem. Generally, structural systems are not designed on the resonant band. It is always a good practice to keep the structural response away from the resonant band. But wave energy converters have an exclusivity. They are generally designed to touch closely to the resonant band. Therefore, the fundamental frequency of VEC is approximately equal to or kept in the band of the dominant peak frequency of the waves. So, once I have this approach in mind in designing a wave energy converter, fixed type will have a problem because they will lose the structural stability. Because they actually sustain the loads, from their strength. Okay, the strength can come from the geometric form, can come from the material, does not matter, but their focus is to resist the loads from the strength, but I want to resist the loads from displacement. So, wave energy converters have taken a new domain of research saying can go for floating wave energy converters. So, the advantages are, as we discussed in the last lecture, the floating wave energy converters can go offshore. It is, they can be commissioned well away from the coast and at deeper water depths. The advantages, as you go deeper and away from the coast, you get very high energy potential. The waves, you get undisturbed energy potential from the waves. So, now at that depth, which is about, I am talking about it approximately 500 meters. At that depth, one cannot install a permanent fixed system because the system design itself will be complex. Therefore, one goes for floating wave energy converter. So, hypothetically, a buoy is anchored to the seabed using cables. We call these cables as technically tethers. So, this is my buoy, let us say. It can be also a point observer. So, now this is my wave line. The buoy has a design draft of some value which keeps the buoy positive buoyant. What do you mean by positive buoyant? Let us try to draw the free body diagram of this buoy. So, let us say the weight of the buoy acts downward and the buoy displaces some volume of water. So, that will give you rise of buoyancy force. Okay. Now, I say by design I want to keep buoyancy force acting upward much higher than the weight acting down. So, what happens? The system will start floating, of course, but you cannot position restrain the system, right? That is the trouble. You cannot position restrain the system. So, now when buoyancy exceeds the weight, then this has got to be compromised by some tension. So, I call this tension as T naught. So, now this will be equivalent to the buoyancy. So, once the tension is removed, once the cable is cut, the system will become freely floating because it is positive buoyant. So, positive buoyancy means Fb exceeds the weight. Neutral buoyancy means Fb equal to weight. Of course, if Fb is lesser than weight or weight is more, it will sink. So, it cannot float at all. So, these two conditions are required for floating, but my design will enable the first condition. So, the T0 value will help me to compromise, adjust the difference between the upward buoyancy force and the downward weight. Okay. Now, I can design a floating system like this. I need not have to have a stiff rigid connection at the bottom. It can be completely floating. Now, by doing this, the advantage is, as we saw in the last lecture, the advantage is it can be hydrodynamically stable. Can be achieved. This can be also checked using something called Matthews stability. So, if you are designing a floating wave energy converter, you must ensure that the Matthews stability parameters are within the limits of flotation and stability. So, I must check the hydrodynamic stability of the design. The greatest advantage what we get in floating energy converter is it is having good recentering ability. The third one of course is it can harness energy in at least 2 degrees. For example, look at this figure. Okay. So, now the body has a freedom to move in the vertical axis. So, the body has heave motion. Of course, the body surges and sway, right. So, the body has surge and sway as well, but heave is restricted by the tether, but surge and sway are free. This surge and sway, let us draw a figure when it surges. Okay. So, the submerged volume increases. So, there is a change in buoyancy, right. When the change in buoyancy occurs, then the T0 will have an horizontal component. So, this will enable recentering. It will try to pull the body back to the equilibrium position. So, 1 degree of freedom which is oscillating or translating is able to harness the energy, and it is also coupled with heave. So, now when surge is coupled with heave and recentering is enabled, so stability is automatically taken care of. So, floating wave energy converters also have this kind of design intuited equilibrium stability imposed system designs, which help us to really achieve the requirement of hydrodynamic stability in addition to harnessing energy at least from 2 parallel degrees of freedom. And now the question here as we discussed is, when there are 2 different degrees of freedom, let us say surge and heave, then the frequency at which they vibrate are different. So, we are now invoking something called multi-body dynamics. Why we say multi-body dynamics? Because there is more than one frequency which is in operation. Why we are bothered about the frequency of vibration? Because we already said the fundamental frequency of the wave has to be tuned with that of the peak frequency of the wave. Now, the question is, when there are more than 2 frequencies, which frequency will you tune? Okay? Now, here comes the design of power takeoff systems. PTO is a mechanical design which is now enabling the conversion of harnessed motion, that is the translatory motion, to rotation, so that I can connect it to the generator for getting electric power. Okay. Now, when we talk about multi-body dynamics, the most important concept which people suggest in literature is that tuning the wave energy converter to multiple frequencies. You may wonder, multiple frequencies arise from where? Is it coming from wave or is it coming from the system? Friends, please note, I am saying tune the frequency. So, tuning is multiple frequency of the system to the dominant frequency of the wave. Okay? So, that is what we are going to do in this. So, clearly OSCAMP and OSGAM 2012 stated from the study that tuning single body wake is comparatively simpler to get maximum expected power, but when we have more than one frequency in operation, that is more than 1 degree of freedom active in harnessing energy, then I must design PTO with different damping frequencies or damping levels. So, now the PTO will take care of this multi-body dynamic intervention in the analysis. So, this will help me to maximize the power output. Having said this, let us talk about the more important matrix in WEC design of multi-body dynamics. Let us say now we are looking for a wave energy converter design, essentially let us say floating and essentially harnessing energy in multiple frequencies. So, we say multi-body dynamics, multi-body in sense there are many WECs integrated together, and even in single WEC there are coupled degrees of freedom which are used to harness energy. So, in such situation, one condition what we must take care of the design is an effective power takeoff system which should be now designed for different damping levels. That is first thing which we must do. The second one is we have to also work out something called harnessing the maximum capture width ratio. Capture width ratios, CWR, is an important index to compare the performance of different wave energy converter systems. This is one of the important performance index. But CWR is not a measure of efficiency. You can have a larger CWR, but still efficiency can be lesser. You can have a small CWR, efficiency can be higher. So, CWR or the capture width ratio is not a measure of efficiency, because efficiency depends on how the system is tuned to the wave frequency, whereas capture width ratio is a geometric parameter. Okay. For example, if I have a wave energy converter and this is my wave approaching, this is the breadth of the design device, okay, which is encountering the wave. I can now say the ratio of B to the wavelength. Okay, we can use even let us say lambda, the wavelength, where lambda is the wavelength which is approximately 1.56 t square for deep waters. Okay. So, if a period is approximately, let us say 10 seconds of a wave, then I can say it is 156 meter. So, if the breadth of the device design is only 3 meter, so the capture width ratio can be 3 by 156, that is the ratio we have. So, to improve this ratio and to have more efficiency, I must have more such designs in parallel. Okay? I have to more such designs in parallel. So, these all B's will all act together to encounter the waves, therefore, this can be higher, therefore, this can be further higher. So, capture width ratio is not a measure of efficiency. Efficiency is related to how good the system is tuned for the frequencies. Capture width ratio is a geometric parameter based on which you design the WEC. Okay. Of course, CWR is an index to measure the energy harvest, the capability of the system to harvest the maximum energy. Okay. So, various WECs under certain conditions show that capture width ratio sometimes, there are capture width ratios sometimes even more than 100%. Okay, you can have more. For example, clearly Bavarit in 2015 and Stansby in 2017, Stansby et al. Showed in the study that capture width ratios can even exceed 1. So, you can have a very interesting design configuration which can be much higher than that of the wavelength which is coming from the encountered wave, and therefore, the efficiency can be much higher. Okay? Therefore, friends, WEC design ideally is controlled by tuning to the dominant wave frequency at the site. So, it is site specific. So, there can be many frequencies encountering by the waves in a site. So, we say dominant or peak wave frequency, okay, and it should be also tuned. When I say P, I can also say 2 pi by omega will also give me the period. So, peak period. So, I can either say peak frequency or peak period. So, I must tune it to this, and also ideally it should have a large capture width ratio. Okay. So, these two concepts, you see, they are actually opposite to what we have in land based design structures. So, we will not like to have a larger encountered space for the wind and wave in a given system, and we will never design a system for its natural frequency to be equal to that of the encountering frequency. Okay. Having said this, this complexity is now to be addressed by the PTO designs. Okay. Having said this, let us say, what are the characteristics that control or govern the PTO design? Okay. To enhance the maximum absorption power, we have two concepts here. I want the maximum efficiency. So, I can either control or achieve this by good geometric design or and or a good PTO design. Okay. Antonio 2007 verified this statement and showed that that's very important idea we have. So, there are varieties of novel PTO technologies available in the literature. There are many novel PTO technologies available in the literature. We are not going to discuss all of them because you can always learn it from the sites. So, I will give you the references. You can refer to Muller 2002. You can also refer to Ivanova et al. 2005. You can also refer to Reinfrank et al. In 2012. So, these papers will help you to understand what are the different possible PTO designs which are. One common thing in all these literatures is that PTO design is controlled mostly by the damping. Therefore, friends, to design an effective PTO, I must have to estimate now the damping coming from the system. So, what are the various sources of damping which can come from the system and how we estimate them? Let us look at the generic classification of a PTO. Let us look at the generic classification of our power takeoff mechanism. So, let us say I have ocean waves which is encountering the system. I design a geometric system. Of a wick. Let us say design a geometric system of a wick. Okay. Now, the primary system has to interfere maximum with the waves encountered by the system. So, what would be the different procedures which can help me in designing PTO? When we talk about the velocity increase, let us say there is a huge velocity increase in the system design, then this will affect, of course, the motion rectification, and you can still harness power. Okay. So, we call this as turbine design. So, turbines work on this concept. Okay. Secondly, if we go for PTO with a piston and cylinder arrangement, and it will have an high pressure rectification, it will have an hydraulic system because I am working on piston motor system. It is an hydraulic motor. We can also connect to rotary generator. Okay. So, this system is what we address as hydraulic PTO. Okay. The third one, if I deal with air compression, which is raised because of the motion characteristics of the wick, then it will have bidirectional rectification. And it can also harness connected to rotary generator. We call the system as pneumatic PTO. Lastly, if I connect the system to a linear generator, and then direct it to the linear generators, is linear electric generator and then take directly to produce electricity. Of course, this also produce electricity. All these will produce electricity. Okay, what we call as a grid connection. Okay, so this one refers to turbines, this one refers to hydraulic PTO, this one refers to pneumatic PTO, and this one refers to linear electric generator concept. Okay, so this figure explains pictorially the generic classification of various power takeoff systems. Let us slightly go ahead and discuss more about the hydraulic PTO. Let us talk about the hydraulic PTO. Hydraulic PTO system, which otherwise referred as HPTO, is one of the most common deployed PTO in wave energy conversion system designs. Okay. This is usually designed for high torque, low speed, oscillating wave energy converter. The suitability is even at low speed this works well. Okay. So, the references could be Drew et al. 2009 and also Jusso et al. In 2019. So, they attempted a design of generic hydraulic power takeoff system fitted to a point absorber, and the design factors which govern the HPTO are the compressibility, because you are working on a piston cylinder mode, compressibility, and next is the pressure loss effects. So, these are some of the factors which account for the design of HPTO. Okay. People have also said that the size of HPTO are relatively large. So, that may be another drawback to deploy HPTO for all kind of WEC systems. Okay. So, there can be some examples where people have used HPTO in point observers. So, examples of hydraulic power takeoff systems in point observers, we can look at something called WaveStar, is a WEC design investigated by Kramer, Hansen and Kramer in 2011 and also Kim et al. In 2019. They showed that the hydrodynamic performance of the device is better for the power takeoff system with hydraulic models, but the limitations were it has got a cylinder which needs to sustain the heave motion also, because the point observer heaves. Therefore, there cannot be a direct drive PTO. There should be an ancillary or a secondary support system required for such PTOs. Okay, that is important. So, many investigators further conducted numerical analysis on different shape of buoys fitted with hydraulic PTOs, and they found that the hydraulic PTOs are found to be better for certain type of operational frequencies, and we can give examples on ocean power technologies, AW energy wave rollers, which is the Scottish Pelamis, they all incorporated PTO with various technologies and use them both on fixed and floating breakwaters and vertical walls. Oscilla Power Triton, which is also a wave energy converter, which is also deploying hydraulic power PTOs for better performance. So, friends, we have learnt in this lecture about the understanding of the primitive factors which controls the design of power takeoff mechanism. We learnt how the hydraulic power takeoff mechanism can be easily deployed with point observers, and we have seen some practical examples in the field where they are deployed. We have also seen a general classification of power takeoff systems as turbine, hydraulic, pneumatic and linear. So, one can choose any form of any classification of PTO for harnessing, because we need wave energy converter uses its translation or motion to capture energy. But the conversion takes place only in the second stage with the PTO. So, this lecture help you to understand that. As we take forward, we will also discuss the detailed design, the mechanical design of various PTOs which are deployable in PEC designs, what we will discuss in the coming up lectures. So, friends, stay continued and listen to the lectures, give your feedback at SwayamPrabha, and this is the course third lecture on marine renewable energy systems, analysis, design and development, offered by Department of Maritime Engineering at IIT Gandhinagar. Thank you for listening to the lecture. Welcome.